In this video, we discuss chapter 3 onwards, linear transformations. First, we have section 3.1. These are the basic properties of linear transformation. First, we have definition of a linear transformation. You might have studied the definition of linear transformation in your degree course. Anyway, I'll write the definition given in this textbook. Let V and W be vector spaces, two vector spaces over a field F. This is very important. When you consider the linear transformation, if you consider two vector spaces V and W, then that field must be common. Okay, so a linear transformation V onto W it's a function from V to W such that means T satisfies some condition T of C alpha plus beta equal to C times T alpha plus T beta. This is the requirement for all alpha comma B. Beta belongs to V and C belongs to the corresponding field. Okay, so if the C comes from the common field F, you can say that this is an element of W and T beta is also an element of W. Then C times the element of W should be defined. Then that's why we our hypothesis is this F is common to this V and W. Okay, so this is the condition for this is the definition for linear transformation. So we can see some examples. If V is a vector space, then you can define a linear transformation I from V to V itself. So since V is a vector space over F, then you can consider this I from V to itself defined by I of alpha equal to alpha for all alpha belongs to V. Obviously, this I satisfies the condition for linear transformation. When you consider I of C alpha plus beta is equal to, by definition, that is C alpha plus beta itself, that can be written as C times this alpha again can be written as I alpha, and beta is nothing but I beta. So this shows that this I is a linear transformation. So we can consider it as example 1. Now we have example 2. The second example is if you consider a field, F is a field, and V is the vector space of all polynomials. Say F. Polynomials are denoted by F here. F from this F into F into F. In fact, that polynomial vector space V is denoted by this f of x, set of all polynomials. Then we can write this is the set of all expressions of the form a0 plus a1x plus etc plus an x raised to n, where ai comes from this f. Okay, the field f. Okay. These are the field f. Here we have field f. Then you define a linear transformation df. df is this d is a function. This d is a linear transformation from f of x to f of x defined by df d of f. Okay, this is f dash. Okay, so once you write the map like this, then you can easily prove that this D is a linear transformation, because when you consider D, C, F plus G, F and G are polynomials, so this can be written as C, F plus G, a derivative of C, F plus G, that is equal to C times F dash plus G dash. So this is equal to C times DF plus DG. This shows that D is a linear transformation on set of all polynomial over a field F. Okay, now, and there are a couple of examples are also discussed in the textbook, so you might have you need to go through all those examples given in textbook. and we can discuss if any if a clarification is needed. Next, I move on to the theorem. This is the existence theorem, existence of the linear transmission. This theorem states that V is a vector space. It's a finite dimensional vector space. Finite dimensional vector space. Finite dimensional vector space over F. This is V, and we are given a basis alpha 1 etc. alpha n. Is an ordered basis for V, and let W be another vector space. W be a vector space, over same field F. But we are not assuming that this W is finite dimensional or not, but the crucial point is we should be finite dimensional. And we have a set of vectors beta 1, beta 2 etc. be any vectors in W. So these are the arbitrary n vectors, need not be basis or any there is no restriction on this beta i's. You can choose all these beta i's as 0 or all the beta i's are same, whatever may be. These are the arbitrary elements of W. Then theorem states that then there exists precisely one linear transformation from linear transformation T anyway from V into W such that T alpha is equal to beta I equal to 1 to n. Okay, so if we are given a basis B of V and an arbitrary n vectors beta 1, beta 2 etc. beta n, then there exists one and only one linear transformation T which maps this alpha 1 to beta 1, alpha 2 to beta 2 etc. alpha n to beta n. This is what you have to prove. To prove this theorem, we need to construct a linear transformation with some relevant properties. So we start with an alpha belongs to V, and then alpha can be written as linear combination of this alpha 1, alpha 2, alpha n, since it is an ordered basis. So that is x1 alpha 1 plus etc. xn alpha n for some xi belongs to F. This is the unique expression for this alpha in terms of alpha 1, alpha 2, alpha n. Now define a map. Define T from V to W such that T of alpha equal to x1 beta 1 plus etc. xn beta n. Okay, this is the image of alpha. So this defines a map from V to W because alpha is an element of V. Then this expression is an element of W as these beta is elements of W. Okay, now we will prove this T is linear transformation and this T is unique. So first we prove T is a linear transformation. In order to prove T is a linear transformation, we need to consider two elements alpha and beta from V. Say this is y1 alpha 1 plus etc. Yn alpha n. Then consider C alpha plus beta, that is Cx1 plus y1 times alpha 1 plus etc. C xn plus yn times alpha n. Now what is T of C alpha plus beta? T of C alpha plus beta is obtained by replacing this alpha I by this beta I. So that is Cx1 plus y1 times beta 1 plus etc. Cxn plus yn times beta n. Now you can write this expression as C times x1 beta 1 plus etc. xn beta n plus this is y1 beta 1 plus etc. y n beta n. Okay, now this is equal to C times this is T of our alpha and this is T of our beta. Okay, this shows that whenever t of c alpha plus beta is equal to c times t alpha plus t beta, this shows that t is linear transformation. Okay, now we have to prove this is unique. Okay, this t is unique. That means when we assume another linear transformation with the same property, say you have the same property u of alpha j equal to beta j for all j is equal to 1 to n, and this u is from the same v to w, then we can prove that this u is same as t. Okay, so in order to prove this u is same as t, we start from u of alpha, uh, any element alpha, then u of this alpha can be written as x1 alpha 1 plus etc xn alpha n. Then this is x1 times u of alpha 1 plus etc xn times u of alpha n, that is equal to x1 times u of alpha 1 is beta 1, so this is beta 1 plus etc xn u of beta n, but this is same as our t of alpha. So this shows that uh, u of alpha is equal to t of alpha for alpha belongs to V. This shows that t and V are the same. Sorry, t and u are the same transformation. This proves the theorem, the existence theorem. That means if we are given a finite dimensional vector space and a basis B, and corresponding to each set of n elements, n vectors in W, there exists exactly one linear transformation which maps alpha 1 to the corresponding beta 1, alpha 2 to corresponding beta 2, and so on.